Hey guys, today we released the fourth skill page on our website about complex numbers as announced in our 500 subscriber special. Moreover, this video is the first part of a mini-series where we begin with introducing some theory to then solve problems with it. In this different format, we encounter many problems small enough to make little exercises out of them. Therefore, we decided to give you the opportunity to solve them on your own, but also uploaded all of the solutions as YouTube Reels in the past few days that we link to in the video description. A motivation for complex numbers is roots of polynomials. Most of the time we are interested in knowing the roots of a polynomial to then be able to factor it. But we all know that over the real numbers we have the inequality x squared is greater than or equal to 0, and therefore, for instance, the polynomial x squared plus 1 has no real root. To solve this problem, we want to introduce a new number or a new symbol, which we call I, or the imaginary unit. And we want to define I in such a way that I squared is equal to -1. We want to be able to work with this new number I, and therefore we need to define how to add and multiply with it. But we may notice that by our previous discussion, we definitely know that I is not a real number, and therefore we have to define a new set of numbers that we work with. And we call them the complex numbers that we denote by the letter C. And this is a set on which we define addition and multiplication, as I said before. And at first, we call its elements A plus BI, where A and B are some real numbers. So we now want to determine how we can add or multiply arbitrary such complex numbers A plus BI. So let's make a small wish list. We definitely want to maintain our usual properties, namely associativity, commutativity and distributivity of addition and multiplication. Moreover, we don't want to throw away the notion of real numbers because they maintain still quite useful. And therefore, the next point on our wish list is that we want to be able to associate the number a plus 0I with, and this is a complex number, with a and r. So we could also just say that a plus 0I is a real number, or in other words, that the set of real numbers is a subset of C, and here is definitely no equality because we have already noted that I cannot be a real number itself. For example, what I mean by this is that we want to be able to do the same stuff in the complex numbers that we can do in the reals. So a plus 0I plus b plus 0I, which we associate with a plus b, and a plus b we associate with a plus b plus 0I, so this should be equal to a plus b plus 0I again. And of course, this was our starting point. We want that I times I is indeed equal to -1. There exists a unique definition for addition and multiplication on that set that satisfies all of these wishes. So at first, we want that a plus bi plus c plus di should be, by our first wish, equal to a plus c plus b plus d times I. For multiplication, we can proceed similarly, and we can write down that a plus bi times c plus di should be equal to ac plus, and here I'm already going to factor out an I because we will have AD plus BC times I plus BD I squared. And now we want to use our third wish, which implies that this all should be equal to, together with the first one again, AC minus BD plus AD plus BC times I. And these 2 points are our full definitions for addition and multiplication of complex numbers. One more useful definition that you will also need for exercise 2 is the complex conjugate. Namely, for real numbers a and b, we define the complex conjugate of a plus bi, which we sometimes say a plus bi bar, to be equal to a minus bi. We start with two small exercises. Check that for complex numbers z1 and z2, their product z1, z2 is equal to 0 if and only if at least one of the two numbers is equal to 0. For the second exercise, you are asked to prove that z1, z2 bar equals z1 bar, z2 bar, and furthermore, for a complex number z, we have z bar is always a non-negative real number. We are now ready to prove our first claim together, and that is that for any complex number z that is not equal to 0, we can find a unique complex number w such that wz, that is of course by commutativity always equal to zw, is equal to 1. To see why this is true, we take a look at our first two exercises. And namely, we see here that z bar is always a non-negative real number. This should motivate us to use the complex conjugate in our claim. In particular, we know that z times z bar divided by z bar, which is some non-negative real number, is equal to 1, which is what we want. Therefore, if z is equal to a plus bi for real numbers a and b, we can write w in this way. Namely, we want that w is equal to a minus bi divided by z bar, and you will have seen in the previous exercise that this is equal to a squared plus b squared. So indeed, this is a solution to our equation, and so we have proven the first part, namely the existence of such a w of our claim. Now let's proceed with proving the uniqueness. And to do that, let us assume that we find some w prime such that wz is equal to w prime z equals 1. Thus, by commutativity, we also get that zw equals 1, and so we can multiply our second equality with w to obtain that w prime zw equals w, and because now zw is equal to 1, this also equals w prime. And so it follows from this assumption that w prime equals w, and therefore we are done. Here I want to note that at this point you can also quickly finish using our first exercise, and I've challenged you to try that on your own. With this new knowledge, let us come back to polynomials. We have originally noted that the polynomial x squared plus 1 has a root at x is equal to I, but moreover, we of course see that because x squared also equals minus x squared, that negative I is a root of that polynomial. And because I is not 0, I and minus I are distinct complex numbers, and therefore it follows that we can factor the polynomial x squared plus 1 into the linear factors x minus I and x plus I. Indeed, a factorization into linear terms is not only possible for x squared plus 1, but over the complex numbers we can do so for every polynomial with complex coefficients. That follows from the fundamental theorem of algebra, which is really important to know in the context of complex numbers, but we do not need a proof here because it is a little bit out of the scope of this video. It is concerned with polynomials with complex coefficients of degree n greater than 0. Because the real numbers are a subset of the complex numbers, this also implies the same statement for polynomials with only real coefficients. And the statement is that we can always find a complex number z such that p of z is equal to 0. Using this and induction, we can conclude that for any such polynomial, we can write p of x to be equal to an times the product of I is equal to 1 up to n of x minus zi for some complex numbers zi. In the second part of this video, we will take a look at particular polynomials and evaluate the exact complex factorization in linear terms. Until then, you can think about one additional exercise that is a really important result about factorizations of real polynomials. Namely, let p be a polynomial with real coefficients.
then we shall prove that there exist polynomials q1, q2 up to qk of degree less than or equal to 2, such that p of x equals q1 of x times q2 of x up to times qk of x. And if you want to see a solution to that problem and more, you can check out our skill page on our website about complex numbers.